You want to think about a bar. Okay? Bar 10 meters long, rotating about this end. Okay? So we've got a 10-meter bar. We want to find the moment of inertia if the density function for the bar is 2 kilograms per meter. Now, if that was all of it, that just means you'd have 2 kilograms for every meter of this bar. The total mass would be 20 kilograms because it's 10 meters long, right? 2 kilograms per meter times 10 meters, 20 meters. But we add something to that. We add 0.01 kilogram per meter cubed times x squared, where x is the distance from the axis of rotation out to whatever point on the bar. So if x is here, then we calculate the density here, okay? So if that's at 7 meters, let's say, if we square 7 meters, we get 49 meters squared. Multiply that by 0.01 kilogram per meter cubed, we get 0.49 kilogram per meter. So our density at this point would be 2 kilograms per meter plus 0.49 kilograms per meter. Okay? And if we wanted to calculate then the mass of a short segment of the bar here, let's say a 10 centimeter segment, that's a tenth of a meter, somewhere in the near vicinity of x equals 7 meters. Okay, well, we multiply 2.49 kilograms per meter by the 10 centimeters, which is, of course, 0.1 meter, and we get 0.249 kilograms. Okay, so we have to understand what I mean by a density function. That's just one example. Think it through. Okay, but you just multiply the density in kilograms per meter by the number of meters, and you get the mass. Because obviously, if you multiply kilograms over meters by meters, the unit's going to be kilograms, which is a unit of mass. And since I'm telling you that means that is the mass of that length, then everything should make a fair amount of sense. Okay? Now, the thing I ask you to do is find the moment of inertia of a short segment of length delta x at position x star. Okay? Make sure we see if that's a star. Okay? And when I say at position x star, well, position x star is just one position. A delta x is a bunch of, it would include a bunch of positions, wouldn't it? So instead of at x star, near position x star. By near, I mean as near as possible, so that the x star would be within this delta x interval. Now, this should be something that's familiar to you from calculus, but maybe not. Okay. So, the mass of the segment is what? Density times length. That's what I told you. I didn't write that definition down, but that should be clear from what I told you before, because I did the example, 2.49 kilograms per meter times a tenth of a meter, right? 0.249 kilograms. That was a density times a length. Okay, so mass of the segment is density times length. What's the density? Well, if this point is x star, then the density is what we get when we plug x star in here for x, right? Okay, so density (2 kilograms per meter plus 0.01 kilogram per meter cubed times x star cubed. So that'll be the density here at position x star. Now if we have a delta x interval, and the intent here, I said near, well, near might be on this side or on this side, but what we really mean is, and I didn't want to write out all the words, a delta x interval that contains that position within it. So you're going to have a delta x interval, and maybe I want to use some colors here. So you have this interval here, okay? And of course you have an interval here on the x-axis that corresponds to a short segment of the bar, okay? So this is your delta x. Hopefully you can read that, but if not, that's what it says. So what's the mass in that region? Well, the density is pretty close to this, and I've written it here, maybe a little hard to read up there, but I've written it here maybe a little more clearly. So there's your density multiplied by the length of the interval. Well, that's delta x. And we call that delta m, the contribution to the total mass of the bar from this increment of the bar, okay? This subinterval of the bar. Then we're trying to figure out moment of inertia, okay? To get the moment of inertia, we multiply the mass, okay, by delta I. I'm talking about the contribution of the moment of inertia corresponding to this delta x interval near this position, okay? That's your delta m, your contribution to the total mass from that interval, multiplied by r squared, because moment of inertia of a point mass is mr squared, where r is the distance at which it's constrained to rotate about some axis, okay? Distance from that axis, well, we know that. Well, what's the distance from the axis at this point? Well, isn't it just x star? Okay? I mean, the axis is at 0, and this is at x star, so it's a distance x star. So it's delta m times x star squared. Now, delta m is this, and we've got to multiply that by x star squared. Well, the expression you get is just going to be this expression, but I'm going to insert the x star squared here. So this expression is identical to this expression, except for the insertion of the extra term, x star squared, here. Now, I've got this then a miracle occurs. The miracle doesn't connect this step and this step. I wrote that down prematurely. The miracle occurs between here and here, and we'll fill in some details. But the miracle is that, okay, well, that means that the total moment of inertia is the integral from 0 to 10 meters of this, well, basically this expression where your x stars become x's and your delta x becomes a dx. And you get this integral, and this integral is very easy to calculate. So I kind of asked everybody to calculate it. Now, there are details here where, we want to sum these up in kind of Riemann sum type thing, but we're not going to do any proofs. But if we sum these up over all such increments, this being the typical increment, well, the bottom line is what we get for one single subinterval, one single increment of this bar gives us the expression we have to integrate, and the limits on the integral will be the limits on the positions that x star could be, okay? We'll talk more about that. Do the integral, understand as much of this as you possibly can.